So the warm-up calculations, let me begin with expanding W tilde J. If you look at this expression, if you take V equal to 0, then it is just 1, and for all values of P, there is no derivative operator acting on that. So sum over P greater than or equal to 0, this is just exponential of this, which is W0J. So for V equal to 0, one has W0J, no vertex. If you do not allow any vertex in the Feynman diagrams, then you will get only the free theory diagrams. Then V equal to 1, so this term is Ig by factorial 3 times this del J cube, and that is V equal to 1, acting on all those diagrams that we drew, the entire stuff for all values of P in W0J. And we had when we studied tree theory, we had diagrammatic representation of W0J. So you can write, therefore, this term is Ig over factorial 3 del over I del J cube acting on W0J. W0J starts with 1, and then the first term is quadratic in J, which is this. Then the second term, then one over factorial 3. And so on. Right? This is what we, if we take V equal to 1, but all values of P, then we end up getting this, where I'm using an hybrid expression. For V, I'm using the mathematical expression, but for the J part, I'm using the Feynman diagrams. It should be okay. We understand what we are doing. And then higher V terms. So let us calculate. So this is, say, let me call this 1, this is 2, and let us calculate 1. So 1 is Ig by factorial 3 del over del J cube acting on this. But you see, this has 2 factors of J. This is nothing but Ij 1 over I delta Ij. These Ij factors are the 2 dots, and then 1 over I delta is the propagator between these 2. Now, since there are 3 derivatives acting on 2 J's, it must be 0, right? So this expression is 0. Similarly, all actually right now. Okay, so let me not generalize it right now. We will have that statement later for vacuum diagrams, but this term is 0. If you have number of derivatives more than the number of J factors, of course that is 0. Now calculate 2 Ig by factorial 3 del J cube acting on half times this. Okay, one difference, I think earlier I included this factor of half inside the diagram. This the symmetry factor is between interchange of these 2, which I took inside. This time I'm keeping it outside. This is the only difference, but we could have done the other way also. Anyway, so so now the expression that if you write it expanded, then it is dz. So we are, our space-time integrals are actually dx, but I'm for for the sake of simplicity, I'm writing this. Similarly, delta x minus y, I will write delta x minus y. It looks like one-dimensional, but we understand what we are doing right now here without any confusion. So then this is an integral of d cube delta cube over delta I z cube. This is what it is. Acting on half integral dx1 d y1 I j x1 1 over I delta x1 minus y1 I j y1, and then d x2 dy2 half. There is a factor of half here. Ij x2 1 over I delta x2 minus y2 ij y2. So I have written, so this is given by this expression, and then for these two I have these two expressions. Each one have a factor of half inside, which is the symmetry between the interchange of two j factors, and an overall factor of half here, which is the symmetry of interchanging between these two propagators. So this is the calculation we have to do, and this is since there are three derivatives acting on 4 j factors, of course, after the calculation is done, one j factor will remain, and three out of these 4 j factors will be absorbed by the derivatives. Now that remaining j can be any of these 4, right? And you can have many variations therefore how these 3 derivatives are acting. However, if you take however, all these results, whichever way, the reason is that there are 2 derivatives which will go to this one of these 2 links. 2 derivatives will go to both the 2 ends, and one derivative will go to only one end, and this result looks the same whichever, if we take either 2 ends of this link or 2 ends of this link, it doesn't matter, the final result will be the same, because whatever the dots that will on which the derivatives are going to act will become z, this one, and the other one will remain free, and in the Feynman rule, every dot has an integration associated with it. So x1 x2 x3, or x1 y1 x2 y2, all of them are integrated over. So 3 of them will be converted into z, and the other will remain, and then it will be accompanied with its with the corresponding integration, and therefore therefore the final result will look same whether whichever combination you take, however way you apply these 3 derivatives on this. But then there are many ways of doing it, so that will give you a multiplicative factor, overall multiplicative factor. So that is how you organize the calculation. So you have Ig then the existing factors in the denominator are factorial 3 times 2 times 2 times 2. There are 3 2's. Okay, and then you have dx1 d then you have dz dx1 dx2 y1 dx2 dy2, and you just take any arbitrary combination of acting this. So let me take 2 derivatives going here and here. So that will give you delta x1 minus z 1 over I delta x1 minus y1, then delta y1 minus z, then delta x2 minus z 1 over I delta x2 minus y2 ij y2 ij y2. That y2 j at y2 remains free. Okay, these are delta functions because your one del I j z is acting on this. So ig divided by factorial 3 times 2 cube, this times a factor of n, the number of repetitions. So let me write that here. So ign so let me separate these factors out. One is factor n divided by factorial 3 times 2 cube, then I times g, and then dz, x1 becomes z, so, and y1 also becomes z. So 1 over I delta z minus z, okay, dy2, and x2 also becomes z, which is 1 over I delta z minus y2 ij y2. So you can reorganize this as in the following manner. It is 1 over s, this factor, n over this factor, the number of repetitions, divided by the factors in the denominator that are already there in the expression. That gives you 1 over s. And then ig times dz, and then I dx jx, that is I'm renaming y2 to x. Okay, and then I have a bunch of propagators, which is 1 over I delta x minus z, 1 over I delta 0, which is z minus z. So this is this is because of the vertex. So this the entire diagram, if you have a diagram, if you want to have a diagrammatic representation of this, then how would it look? So there is a dot here because there is a source here. So there is a dot, then x goes to z, there is a propagator from x to z, this is a dot, and then there's a propagator from x to z, and at z you have a loop with this as a vertex factor. So this is a vertex, there is a vertex, and then there is a loop z to z. Okay, so this is the vertex factor, this coming from this vertex. This is the source. This is the source factor. This is source. This is vertex. And these two are propagators. Which are here and here. And then 1 over s is by definition n over factorial 3 times 2 cube. We have to figure out what n is. Once we know what n is, we know the symmetry factors. So therefore, we can write down the Feynman rules. And so let me write down the Feynman rules now, which will be true for all the other calculations or all the other terms in W tilde J. So draw all possible topologically distinct diagrams using dots, propagators, and vertices. Then, to find the mathematical expression corresponding to that, for each source, write I integral dx jx. For each source, you have a factor of I times j and integrate over the location of the source. Number 2, for each vertex, write Ig times integral dz. The location of the, for each vertex, you write I times g and then integrate over the location of the vertex. Number 3 is for each propagator, write 1 over I delta x minus y. And finally, number 4, multiply by the symmetry factor. 1 over s. So for the particular, so what we have to yet to learn is how to figure out this symmetry factor. So let us calculate this in this particular example that we just worked out. So calculate 1 over s for this particular diagram. So in this diagram, you have 3 derivatives. Let me pictorially draw them like this. There are 3 links coming from the vertex, and then there are 2 propagators with the j's. How many ways could you so the ways the derivatives will act, all possible ways, and the derivatives are going to act on those j's. The j's are sitting here, 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 and these are the derivatives, right? So these are the derivatives and these are the j's. Now it will happen just by the rule for the derivatives. It will happen in all possible ways, and we have to count the number of possibilities. So this, what we can do now, so we discussed the topological property of this particular contraction, or this, look at the topological property of this diagram. In this topological, from this, you know that 2 derivatives are going to act on the 2 dots of the same propagator, and 1 derivative is going to act on one of the 2 dots of the other propagator, right? So 2 derivatives will be acting on 2 dots of the same propagator, either this one or this one, and 1 will be acting only on 1 dot of the other propagator. So that one, it is easier to do the calculation, that to enumeration that way. So single out that particular one, which is going to hit only 1 dot of a propagator. That one can be chosen in 3 ways. So you're calculating n. So that one link or one derivative out of these three derivatives, you have to choose one derivative that will go to a single dot. Okay, so that can be chosen in three ways. Once that link is chosen, it has to either act on a dot in this link or this link. That is two ways of doing that. So multiply by 2. Once it has chosen the link on which to act, it has to, then you have to choose which dot to act on, because it will act only on one dot and the other dot will remain free. That it can act on like this and or like this. So that gives you another two possibilities. So that way you have now exhausted the possibility of this. The topological variation, the topological character says of the diagram says that now this has to remain, this dot has to remain free, and these two are now supposed to go and hit on this. Now that can again happen in two ways, because it can go like this or it can go like this, right? You can flip, interchange. So that is another factor of 2. So this is 3 times 2 cube, and therefore 1 over s, which is n by 3 factorial times 2 cube, is 3 over 3 factorial, that's half. So s is equal to 2 for this diagram. That means for this diagram, s is equal to 2. Okay, now that completes the calculation of this term totally. Yeah, we have now calculated this term completely. This is the expression. This is half, and this is the expression. So the same basic methodology should work in for more complicated diagrams or calculations as well, for all the higher order terms. This establishes this for all the higher order terms, you have just more number of these derivative factors and more number of links, but it is the same thing. It is just the counting of how you link a derivative, how you link a particular derivative with a j among the possible j's that are there in the links. So this is basically this is the method of calculation. So that tells that it's every term in w tilde j has a diagrammatic representation where the diagram is a topological diagram. That is the conclusion. Just from the nature of this calculation, we conclude the basic character of calculation remains same for all other terms in w tilde j. This establishes that all terms have diagrammatic representation where these are topological diagrams. So now our evolved approach will be, for more complicated terms in w tilde j, is to write all possible topologically inequivalent diagrams. And that requires us to classify various terms, because we need to say that what kind of diagrams are we looking for. And so there are certain properties of the terms that we need to fix so that that can tell us what kind of topologies we are looking for. So the approach write various terms by drawing all possible topologically inequivalent diagrams, and then applying Feynman rules to get the corresponding mathematical expressions. Exactly what we found in the free theory. The same thing is happening here as well. So this means topological, so we need to classify terms so that the topologies of the diagrams can be classified. So this requires us to understand the topological classifications of the diagrams, and therefore we should classify the terms. So this requires us to classify various terms in W tilde J in order to require classify, this requires us to classify various terms in W tilde J according to topologies. This is what we shall do next.